Hey everybody, welcome to interviewBlog. In this video, we will be covering the question first value that equals index. So the question gives us an array of sorted distinct integers and it asks us to determine the index which is equal to the value that is present at that particular index. For example, in this given input array, we can see that the values 2 and 3 are equal to the indexes at which it is present. But the question wants us to write a function to determine the first value that equals index. Hence, in this case, our function has to return 2 as our answer. So hope you understood the question. Let us now see how to solve this problem. So as soon as I hear this problem, my first solution or my naive solution to solve this problem would be traversing the entire array from the beginning, and at each index, I'll be checking if that particular index is equal to my value that is present at that particular index. So for example, in this case, I'll be traversing the array from the beginning, and at the 0th index, I'll be checking if the 0 is equal to the value present at that particular index, which is -3. Since 0 is not equal to -3, I'll continue to traverse the array. Now I'll be checking if this 1 is equal to -1. And since it's not equal, I'll continue to traverse the array. Now you can see that my index value 2 is equal to the element that is present at that particular index, which is 2. And since I have encountered the first value that is equal to the index, my function should return this particular index as my answer. So this 2 will be my answer. So let us now analyze the complexity of our naive solution. The time complexity of our solution tends to be big O of n, where n is the number of integers in the given input array. So why is the time complexity big O of n? Let us now consider an array that contains 10, 11, and 12. And the indexes of this array would be 0, 1, and 2. Now, to solve this problem, I'll be traversing this array from the beginning, and at each index, I'll be checking if that index value is equal to the element that is present at that particular index. So after traversing the entire array, we will come to know that there is no index that equals to the value present at that particular index. Hence, in this case, our function should return -1. So we'll be traversing the entire array, and hence our time complexity tends to be big O of n. Now the space complexity of our naive solution tends to be big O of 1. So why is it big O of 1? Because we are not using any extra space. We are just traversing the array to solve the problem, and hence our space complexity tends to be big O of 1. So can we do better? The question says that the given input array consists of distinct sorted integers. So since the given input array is sorted, this problem can be solved using binary search. So hope you are familiar with binary search. If you are not familiar with binary search algorithm, I have provided the video link in the description. Please do check it out. So this is the modified binary search algorithm. Please note that there is no target value here. Instead, we will be checking if the index is equal to the value that is present at that particular index. So according to the algorithm, we will be using 2 pointers, that is the left pointer and the right pointer. So the left pointer points to the 0th index of the given input array, and our right pointer points to the last index of the given input array. Now we'll be calculating the middle index as our left index, which is 0, plus our right index, which is 6, rounded and divided by 2. This gives us 3. So our middle index will now point to the element 3. So now, since our middle index is equal to the element that is present in the middle index, we will be ending up in this case. And now we have to check if the previous index is greater than the previous value. That is, the previous index in our case is 2, and the previous value in our case is 2. Now, is this 2 greater than this 2? We can see that this 2 is not greater than this 2. So we will not be returning this middle index. So why are we not returning the middle index? As you can see, the solution to this problem is 2, since 2 is the first value that equals to its index, and we are now present in this 3. Hence, we will be ending up with this statement, which is whenever our middle index is less than or equal to middle value. This statement has failed, and now our middle index is equal to our middle value. Hence, we can see that there is some element which is present in this part of our array where the value is equal to its index. So now we'll be updating our right index as middle index -1. That is, we will be moving our right pointer to here, and we will be eliminating this part of our array. So now our left index is 0 and our right index is 2. Again, we will be calculating our middle index as left plus right rounded and divided by 2. In this case, our middle index would be 1. Now we can see that our middle index is greater than our value that is present at that particular index. Since 1 is greater than -1, we will be updating our left index as middle index plus 1. So I'll be moving my left pointer to the first index and I'll be eliminating this part of our input array. So now our left pointer points to the first index and our right pointer points to the second index. We will again be calculating our middle index. Our middle index would be 1 plus 2 rounded and divided by 2. In this case, our middle index would be 1. So now our middle index will point to the first index value. Now we can see that our middle index is again greater than the value that is present in the middle index, which in our case is -1. So now, since 1 is greater than -1, we will be updating our left index as middle index plus 1. So now my left pointer will be pointing to this 2 and I'll be eliminating this part of the input array. So now we can see that both my left and right pointer points to the second index. So I'll be recalculating my middle index as left plus right rounded and divided by 2. So in this case, my middle index will be 2. So now I'll be checking the middle index and the element that is present in the middle index. While comparing these two elements, I can find that our middle index is equal to the element that is present in the middle index. Hence, we'll be looking at this statement. And in this case, we have to check if the previous index is greater than the previous value. Now, our previous index is 1 and our previous value would be -1. Since 1 is greater than -1, we have to return the middle index. That is, the element that is present in the middle index 2 is the first element that equals to its index value. Hence, our solution for this problem would be 2. So each time when our middle index is equal to middle value, why do we check whether the previous index is greater than our previous value? We check this condition to verify whether the particular middle value is the first value that equals to its index. That is, when our middle pointer pointed this middle element, which is 3, we checked whether the previous index is greater than the previous value. And since both of them are equal, we then traverse the left part of our given input array to find the first value that equals to its index. Whenever the previous index is greater than the previous value, it means that there cannot be any value before the middle value which equals to its index. For example, let us consider this part of our given input array. In this case, we have found that our middle index is equal to the middle value, and we are checking whether this previous index is greater than this previous value. Since our previous index is greater than the previous value, we have returned the middle index. Since this previous index is greater than this previous value, there also cannot be any number before this previous index that can be equal to its index value. Because for each step before the previous index, the index reduces by -1, whereas the value reduces by at least -1, since the integers of the given input array are distinct. So in our case, in this part of our array, we can see that there cannot be an element 0 which equals to the index at that particular position. Since we have a -1 here, the minimum number that can be present in this position is -2. Hence, this condition is used to find the first value that equals to the index. So let us now solve this example. First, we'll be calculating our middle index as left index plus right index by 2, and our middle index would be 0 plus 6 rounded and divided by 2, which will point to this 3. So now we'll compare the middle index with the element that is present in the middle index, and since both are equal, we'll be checking if the previous index is greater than the previous value. And here the previous index is 2 and the previous value is 2, and since both of them are equal and the previous index is not greater than previous value, so we will be ending up with updating the right index as middle index -1. So our right index will now point to the second index. So now again we will be recalculating our middle index as our left index plus right index rounded and divided by 2. In this case, our middle index would point to the first index And now we'll be checking our middle index and the element that is present in the middle index. We can find that both of them are equal, and hence we will now again check if the previous index, which in this case is 0, is equal to the value that is present in the previous index, that is 0. Since both of them are equal, so we will now again update the right index as middle index minus 1. So now we will be updating our right pointer to the 0th index. Now we will again be recalculating our middle index as left index plus right index rounded and divided by 2. Now our middle index will point to the first element of the given input array. So this is a special case since there is no previous index or previous value for this particular element. Hence, we should handle this case separately. That is, whenever our middle index is equal to our middle value and our middle index is equal to 0, at this point, we have to return the middle index. So in this case, we will be returning the middle index, that is 0, as our answer. Whenever the whole traversal is completed and we do not find any index that equals to its value, we have to return minus 1. So hope you understood the solution. Let us now analyze the complexity of this solution. The time complexity of our solution tends to be big O of log n, and the space complexity of our algorithm tends to be big O of 1. So why is the time complexity log n? Because we have modified the binary search algorithm to solve this problem. That is, in this particular case, we will be eliminating this part of our array first, and then we will be eliminating this part of our array to find the answer. Since we are eliminating half of the given input at each iteration, our time complexity tends to be big O of log n. And since we do not use any extra space and we finish the solution by using just pointers, our space complexity tends to be big O of 1. So hope you understood the solution. Let us now implement it in code. All right. So we got our first value that equals index function defined, which takes in an array. So as discussed earlier, in our naive solution, what we'll do is we'll be traversing the array from the beginning, that is for I in range len of array. We'll check if the index I, or let me have it as idx, if index is equal to the element present at that particular index. In this case, we have to return the index. If there is no value that is equal to the index, in this case, we have to return -1. So this solution has a time complexity of big O of n and a space complexity of big O of 1. So why is the time complexity big O of n? Because we are traversing the array from the beginning, and whenever there is no value which equals to its index, we'll be traversing the entire array and then we'll be returning -1. Hence our time complexity tends to be big O of n. And the space complexity of our solution tends to be big O of 1 because we are not using any extra space in our solution. We are just traversing the array to find whether there is a value that equals to the index. All right, so let us now test our solution. So this is the first test case. So this test case has to return this 2 as the answer. So let us now run our solution to check if this 2 is returned. And yes, we have got 2 here. So this is the answer for this test case. Now let us run this test case. In this test case, the answer should be 0. So let us now run our test case. So yes, our function has returned 0. So now let us run the next test case. So now for this test case, the answer should be the last element, that is 4. Let us now run our test case and our function has returned 4. So let us now run the last test case. In this test case, the answer should be -1 since there are no value which equals its index. And yeah, our function has returned -1. Hence, the solution works fine. So let us now implement the modified binary search solution, which runs in logarithmic time. So first, I'll be having 2 pointers. The left pointer will point to the first element of the given array, and the right pointer will point to the last element of the given array. So len of array minus 1. Now what will I say is, while my left pointer is less than or equal to right pointer, I will be iterating the given input array. In this case, I'll be calculating the middle index. So my middle index would be my left index plus right index rounded and divided by 2. And my middle element will be the value that is present in the middle index. Now I'll be comparing my middle index with the middle element. So if my middle index is greater than my middle element, so in this case, I will have to eliminate the part of the array which is left to the middle index. So I will be updating my left index to middle index plus 1. Next, if the middle index is equal to the middle element and my previous index, that is my middle index minus 1, is greater than the element that is present in the previous index, that is my middle index minus 1. In this case, I'll be returning the middle index. Next, if my middle index is equal to the middle element and my middle index is the first index, in this case, I'll be returning my middle index since there will be no previous index in this case. Else, I'll be updating my right index as middle index minus 1. So once my traversal is completed, if I couldn't find a value that equals to the index, in this case, I have to return minus 1. So this will be my solution. So this solution has a time complexity of big O of log n and the space complexity of big O of 1, where n is the length of the input array. So let us now test our solution. So first, as discussed already, this solution has to return this 2 as my answer. So let us now run our solution. And yes, our function has returned 2. Next, for this test case, our function has to return 0 as the answer. So let me run the solution and our solution has returned 0. Hence, this test case has been passed. Next, for this test case, our function has to return 4 as the answer. Let me run the solution and yes, our function has returned 4. And in the last test case, there is no value which equals to its index. So our function has to return minus 1. So yes, our function has returned minus 1. Hence, our solution works fine. Hope you understood the problem. Do subscribe and check out our channel for more videos. Thank you so much.